Hi, in this video I am going to solve the problems related to Lecture 3 on Basic Linear Algebra. In the description below this video, you find the link to the PDF file containing these problems. You can also find the links to these notes that right now you can partly see on your display as a PDF file as well as a GoodNotes file. Okay, let us start solving the first problem. Determine the value of this sum if the matrices A and B are equal. Okay, so if you look at this sum, we have I, which is the counter of this sigma, and it runs from 1 to 2, so it takes only two values, 1 and 2, but A and B are missing yet. So we need to equate these two matrices because of the assumption that these two matrices are equal, and find the values for A and B, plug them in this sigma and expand it and find the value. Okay? So we want to do that here. So when A is equal to B, it means that, because of course the order, this matrix is 2 by 2, this matrix is 2 by 2, so from the order point of view, they match. So we need to make the entries to be correspondingly equal to each other. Okay, so then this implies that A minus B has to be equal to 1, and then minus 2B has to be equal to minus A, 2A minus 2 has to be equal to A, and 1 has to be equal to B. Yes? So all of them should be simultaneously satisfied. Okay, so this entry number 1 should match with this one, this entry should be equal to that, this entry should be equal to this, and finally this entry should be equal to that one. So then, for example, I can immediately realize that of course this is the value for B. So B is equal to 1. But from here, I can immediately solve for A, for example. So then it becomes 2A minus A is equal to 2. Then it means that A is equal to 2. Okay, but of course, before accepting them, we need to check them that if the other ones also are true, yes? So, because if that's not the case, then it means that these two matrices cannot be equal in the first place. So if I put A2 and B1, so 2 minus 1 is actually 1, so that's also correct. And minus 2 times B becomes minus 2, minus A also becomes minus 2. So actually these numbers that we found for A and B are indeed the solutions of this system of 4 equations in 2 unknowns. Okay, so these are the solutions. Now my question mark here is the sigma of this combination IA plus B, where I goes from 1 to 2, but now we know that A is equal to 2, so it becomes 2I plus B is 1. And then I goes from 1 to 2. So then it means that, this is equal to, I put 1 instead of I, so it becomes 2 times 1 plus 1. And then I put 2 instead of I, it becomes 2 times 2 plus 1. And then it becomes 3 plus 5, and the answer is 8. So the answer to this problem is 8. Okay, so this problem was so simple. Now assume that I have asked you to calculate this sum. For example, instead of running I from 1 to 2, let us say I run I from 1 to 100. Okay, so then assume that, let me change my color. So assume that we want to answer this question. Okay, what is this sum? I goes from 1 to 100. Okay. So then, of course, if I want to calculate this is also simple. So I would write I goes from 1 to 100. And instead of this little a, I substitute 2 and I replace b with 1. Yes, so it becomes 2i plus 1. Okay? And then you can immediately realize that this is the sum of an arithmetic progression including 100 terms, because I runs from 1 to 100. And then the first number is what? If I plug 1 instead of I, it will give me 3. The next one, if I put 2, it gives me 5. So I am adding odd numbers up to, finally, if I replace I with 100, I will get 201. Yes? And hopefully you remember the formula for the sum of an arithmetic progression. So the sum of the first n terms is equal to n times the first term plus the last term divided by 2. Yes? So here, how many terms are involved? 100 terms. And the first term is 3, the last term is 201, and then divided by 2. Okay, and then if you calculate this, 200 and divided by 2 becomes 50 times 204. And of course, if you multiply this, then it becomes 10,200. Okay, so you see that even if I have asked you to calculate the sum in a bigger range for the counter, it was easy because this sequence actually forms an arithmetic sequence. And then we have a formula for the sum of the first n terms of an arithmetic sequence. Okay, next problem. Solve the matrix equation that you see here for the unknown matrix X, in which A, the matrix A with entries little I sub I j, and capital B with entries little b sub I j, are both square matrices of order 2, and the entries are defined using these relations. So, and of course, this I is the identity matrix, but it is because it is mentioned that all these matrices of order are square matrices of order 2, so implicitly it means that this identity matrix is also the identity matrix of order 2. Okay, so I would solve this problem just starting as if that's just a normal equation for an unknown x. Yes, 4x minus 2a plus b is equal. On the right hand side I multiply 2 inside. This is possible because of the properties of multiplication of a number by a matrix, which was called scalar multiplication, and then I have a minus b at the end. Okay, so what I do, I actually move 2x to the left, so it becomes 4x. Moving 2x to the left gives me minus 2x, and then I will move everything to the right. So minus 2a goes to the right, b goes to the right. So I already have 2i here and minus b there. So I would have 2i minus b, and I move minus 2a to the right, it becomes positive 2a, and I move b to the right, it becomes negative b. And I have 4x minus 2x can be written as 2x, and on the right hand side 2 minus b and minus b becomes minus 2b. Okay, so I will have 2i plus 2a minus 2b. Yes? On the left hand side, on the right hand side, I can factor a 2 out, so it becomes 2 times I plus a minus b. All the things that I am doing here is exactly like the operations that I do with numbers. The reason is that because scalar multiplication, matrix addition, matrix subtraction, all have the same properties of numbers. Okay, we have already discussed that in lecture 3. So I divide both sides by 2. So this means that my unknown matrix is I plus a minus b. But now I need to explicitly calculate my matrix X. I already know I, so I is the 2 by 2 unit matrix, which is actually 1, 0, 0, 1. And then my matrix A is a 2 by 2 matrix, so matrix A is this matrix, A1, 1, A1, 2, A2, 1, and A2, 2. Yes? So what I need to do, I need to calculate these things explicitly, these entries. Exactly the same thing for B. Yes, so this is B11, B12, B21, and B22. Yes? Okay, so how should I calculate them? Using the formulas given here. So a sub ij is equal to I plus j squared. Yes, so if I want to use the formula, I will get a is equal to a sub 1, 1. So instead of I put 1. Instead of j, I also put 1. But when I calculate this one, it becomes 2. So the first entry is 2. And now for the next entry, I index is 1, j index is 2. So if I put them here, 1 plus 2 to the 2 becomes 5. So this is 5. And then the same thing for A21. So I need to replace I with 2, j with 1. This times I will get 3. And then finally for A22, I replace both I and j with 2. So it becomes 4 plus 2 is 6. So this is my matrix A. Oops. This is my matrix A. And then I will also calculate the matrix B. Yes? So if I calculate matrix B, I need to use the formulas for matrix B. So B sub 1, 1 is 1 to power 2 minus 1 to power 2, which gives me 0. And then for this one, I index is 1, j index is 2. So 1 to the 2 minus 2 to the 2 is minus 3. And then for B21, I index is 2, j index is 1, so it becomes 4 minus 1, positive 3. And then finally, both indices I and j are equal, so this difference becomes 0. Okay. Yes? So these are my matrices. So what I can do, I can just plug them here for this relation. Yes, I know I know A, I know B, so my X can be calculated simply as, so I will have this matrix 1, 0, 0, 1, the identity matrix, and then I will have plus matrix A, I already calculated it, it's 2, 5, 3, and 6. Yes, and then finally, I don't know, sometimes this application, yeah, okay. So the next one is negative. Matrix B is 0, minus 3, 3, and 0. And now I need to simplify this expression as a 2 by 2 matrix. So if I add 1 to 2, it becomes 3. Negative 0 is positive 3. The next one is 0 plus 5 is 5. Minus 3 is 8. And then I have 0 plus 3 is 3, minus 3 is 0. And then finally I have 1 plus 6 is 7, minus 0 is 7. So that would be the answer to this problem. This is the matrix that I was looking for. Okay? We can also go and see the following problem. Here we want to simplify this expression as much as possible. So here, this cosine of theta is just a number, and that's a 2 by 2 matrix. I want to multiply this number into this matrix. So we know the rule. I need to take this number and multiply it on each entries here. Do the same thing here for sine on this matrix. And then I will get 2 by 2 matrices, then I add them as usual. Yes? So let us start doing that. Okay, so first I multiply this cosine inside, yes? So if I multiply this, it becomes cosine to the power of 2 theta. The other entry becomes cosine theta multiplied by sine theta. The other one becomes negative cosine theta sine theta. And the other one becomes cosine squared theta again. Yes. Okay, and the other one, if I multiply this, it becomes sine squared theta minus sine theta cosine theta, and then sine theta cosine theta, and finally sine squared theta. Yes? Okay, now let us not use this feature. Okay, now I want to add these two matrices together. So what can I do? I have to add this entry by entry. So the first one should be added to this one, but we know a famous trigonometric identity: cosine squared of an angle plus sine squared of the same angle is 1. And then this expression and this expression should be added together, but they are opposite ones, so they will cancel each other and we'll get 0. The same is true for here and here, so that's also 0. And then this one added to this one using this rule, again, it becomes 1. So as you see, this is just simply the identity matrix 2 by 2. So I can write it as I, and I put the subscript 2 in showing that this is a 2 by 2 matrix. Okay? Okay, problem D. Let A and B be square matrices of order 4 such that 3 times A plus 2 times B is equal to I, identity matrix. Of course, this is the 4 by 4 identity matrix because A and B are given to be 4 by 4, so this combination is a 4 by 4 matrix, and if it is supposed to be equal to an identity matrix, that identity matrix should be the 4 by 4 identity matrix. On top of that, we know that 5 times A minus 2 times B is this given matrix. Determine the entry of this matrix, 4 times A plus 8 times B, that lies on the second row and third column. Of course, I can use this and that to solve a system of equations for the unknown matrices A and B, and find A in its entirety, find B in its entirety, and put them here, and find this matrix. And then go and read the entry on the second row and the third column. But the whole point of this exercise is to avoid this calculation, because you're only interested in very particular entry of this matrix, which lies, of course, on the second row and the third column, according to the problem. So I really don't need to find A and B in their entirety. Okay, so I can just be specific and try to find these entries using this information. So of course this will save a lot of calculations for us. Okay, so what I want to do, let me start with my question mark. So my question mark is this: I am interested in the entry of this matrix which lies on the second row and third column. So that is my question mark. And now we know that I have the sum of two matrices and I am interested in this particular entry, so it becomes the entry of this matrix which lies on the second row and the third column. So it means that I need to take the corresponding entry from this, take the corresponding entry from the second matrix, which is this one, and then add them together. Here, of course, you see this addition is between two matrices, so that's a matrix addition, and this addition is between two numbers, so that's just an addition between two real numbers. And we also know that from what we learned in lecture 3, that if I have a number multiplied by a matrix, that number should be multiplied on all the entries of that matrix. So then it means that this becomes 4 times the corresponding entry of matrix A plus 8 times the corresponding entry of matrix B. So in order to be able to answer this question mark, I need to find this value and this, and then put them here and then calculate. Okay, so you see that we are not interested in the matrix A in its entirety. Yes, I only care about one very particular entry of matrix A, and the same for matrix B. Okay, so let me start from this assumption that I know that 3A plus 2B is equal to B, the identity matrix. Okay, if two matrices are equal, any entry of the matrix on the left hand side should be equal to the corresponding entry of the matrix on the right. So here I am interested in the entry on the second row and third column, so I consider this scenario. Okay, and let us not explain everything, so this is completely similar, that this can be expanded into this form: 3 times A 2 3 and then I will have 2 times b sub 2, 3. And then of course you remember this is the identity matrix, so entries are given by the chronicle delta, so the entry 2, 3 is delta 2, 3, but because 2 and 3 are not equal, this chronicle delta is 0. Of course it is very trivial, it's 0. So that's one equation that will help me to solve this problem. Yes? Now let us start using this piece of information. I know that this matrix is equal to this, so what does it mean? It means that the entry 5, by looking at that information, I can immediately read it here, yes? So if I ask you what is the entry 2, 3 of this matrix, you would say this matrix is equal to this. This is the second row and this is the third column, so the intersection is this entry, which is 1. So from that I can immediately see that this is 1, and I can use the expansion again as I did before, so it becomes 5 times this entry of A minus 2 times the corresponding entry of B, and then I have it equal to 1. Yes, so this is also another equation that will help us to solve the problem. And then you suddenly see that this is a system of two equations between two numbers. One number is this entry and the other number is this entry. So for example, I can use the method of elimination or substitution to simplify, to solve this system. So let me call, for example, this one number 1, and let me call this one number 2. Okay, so from number 1 I can immediately realize that, for example, the entry B 2, 3 is equal to minus 3 over 2 entry A 2, 3. Yes? So I took this to the right hand side and I divide by 2, so I will get that expression. And then I go here and replace this with what I got here. Yes? So what I get is this. So I will use number 2, then I will write 5 times this entry minus 2 times minus 3 over 2 A 2, 3 is equal to 1. But then I can simplify. This 2 and this 2 are gone, so minus minus becomes 3. 3 plus 5 is 8. Yes, so this becomes 8 times this entry is equal to 1, and finally I get my entry to be equal to 1 over 8. Yes, so this is the entry that I was looking for, one of the entries. Yes, and now what I do, I will take this one and put it here. Yes, then I can find this in the one which is left. So B 2, 3 is equal to minus 3 over 2 multiplied by 1 over 8, which becomes minus 3 over 16. So it becomes minus 3 over 16. So that's also the next entry that I wanted to find. Now everything is ready. So here I go to this question mark. Instead of this, I put 1 over 8, and instead of this, I put this number and calculate that combination. Yes, so let me make it a little bit smaller. Okay, so the question mark is equal to, so therefore the question mark is equal to, let me write it from here, is equal to 4 times this entry, but this entry is 1 over 8, so it's 4 times 1 over 8, and then I will have 8 times minus 3 over 16. So then it becomes 1 over 2 minus 3 over 2. Yes, and then it becomes minus 1. So it means the question mark that I was looking for is just minus 1. Okay? Okay, problem E. Determine matrices x, y, and z such that x plus 2 times y plus z is equal to the 0 matrix, 3 times x minus y plus 2z is equal to the identity matrix, and x plus y minus 2z is equal to this 2 by 2 matrix. From this last equation, we immediately realize what the order of these matrices are. All of them should be 2 by 2 matrices. Otherwise, this combination cannot be equal to a 2 by 2 matrix. Now that we know that all these matrices are 2 by 2, if we go back and look at this equation, we immediately realize that this is the 2 by 2 zero matrix, and this is the 2 by 2 identity matrix. Okay, now if you see the operations involved in this system of equations are just matrix addition, matrix subtraction, and scalar multiplication, multiplying a number by a matrix. And in the previous lecture, we actually learned that the properties of these operations are exactly identical to the properties that we expect for numbers. So in principle, I can just pretend that these x, y, and z are just numbers and use the methods and tricks that I was able to use for solving the system of 3 equations in 3 unknowns for this case as well. Yes, and then of course you know that the general strategy to solve systems of equations is method of elimination. But sometimes if we are observant, we can save time with respect to regarding the calculations. Yes, for example, here if you see this equation and this equation, if I add them, not only the y cancels out, but also z will cancel out, and then I am left with just one unknown x, and then I can solve that and find x. When I find the x, I put it back in 2 of these equations, then I will get a system of 2 equations in 2 unknowns, and I can solve that system and find the other variables. Okay, so let us just do it here. So as I told you, I will start from, of course it doesn't matter which 2 of them you will take, but as I told you that here it's much easier to take these 2. So I will write the first equation, 3x minus y plus 2z is equal to the identity matrix, and then we learn that this identity matrix is the 2 by 2 identity matrix. Yes, and then we also have the other equation, which is x plus y minus 2z is equal to this given matrix. 1, 2, minus 1, and 3. Yes? Okay, now if I add them, this y and that y are cancelled, this 2z and minus 2z are cancelled, 3x and x becomes 4x is equal to, then I will have this matrix here. So 1 and 1 will be added, it becomes 2, 0 and 2, it becomes 2, 0 and minus 1 becomes minus 1, and 1 and 3 becomes 4. Yes? And then what I can do to find x, you know that I can multiply both sides by 1 over 4. So the left hand side becomes x and the right hand side becomes 1 over 4 multiplied by this matrix 2, 2, minus 1, and 4. But of course I prefer to multiply this number inside. So then what I get is that x is equal to if I multiply 1 over 4 inside, it becomes 1 over 2. The next one also becomes 1 over 2, and then I will have minus 1 over 4, and then finally I will have 1. Yes? Okay. So this would be my x matrix. And now I can plug this back into 2 of these equations. So for example, let us choose this one and that one. Yes? So here you see that if I move x to the right hand side, it becomes negative x, but the 0 matrix negative x is just negative x. So I will get 2y plus z is equal to negative x. So this becomes 2y plus z is equal to negative x. Negative x is the opposite of this matrix, so I need to multiply the entries by just a negative sign. So it becomes minus a half, positive 1 over 4, and negative 1. Yes? So this is the matrix that I get. And then let me try to use this one as well. Here I keep y and minus 2z on the left hand side, and I move x to the right hand side, it becomes negative x. So this matrix minus the matrix x should be written down. So I will have y minus 2z is equal to this matrix 1, 2, minus 1 and 3 minus matrix x, which is 1 over 2, 1 over 2, minus 1 over 4 and 1. Yes? And then let me simplify this. So here I have 1 minus a half, which becomes 1 over 2. 2 minus a half is 3 over 2. Minus 1 minus 1 over 4. It becomes minus 3 over 4. And then I will have 3 minus 1, which is 2. Yes? So let me double check that one. Yes, that's correct. Okay, now you see that I have a new system of two equations and in two unknowns, y and z. Again, I need to use the method of elimination to get rid of one of these variables. So here what I can do, I can multiply the first by 2. Yes, why? If I multiply this by 2, it becomes positive 2z, and then if I add it here, these 2 will cancel. So multiplying by 2 is a good idea. So then it becomes 4y plus 2z is equal to, and if I multiply the right hand side by 2, it becomes negative 1, 1 over 2, and negative 2. Yes? And now I add this equation and this equation side by side. But if I add this one to this one, this 2z and minus 2z are cancelled. 4y plus y becomes 5y. Yes? And on the right hand side, I have to add these two together. So I need to add this and that. Okay? So the first entry should be added to the first entry, which gives me minus a half. The second one to the second one gives me positive 1 over 2. The next one is minus 1 over 4. And the next one is 0 if I add them. Yes? And I multiply by 1 over 4. 1 over 5, then it becomes minus 1 over 10, 1 over 10, minus 1 over 20, and 0. So this is also the second matrix I was looking for. And now, when everything is clear, I can put it back into one of these equations and find z, for example. I can put it here. Okay, so z is equal to this matrix minus 2y. Yes, so z becomes equal to this matrix here. So let me write it down. So it's minus a half, 1 over 4, minus a half, minus 2 times y. So it's minus 2 times y, I just got it here. It's minus 1 over 10, 1 over 10, minus 1 over 20, and then I will have 0. Yes? Now, what should I do? I need to calculate this and simplify it a little bit more. So let me write the first matrix. And I multiply 2 inside, so it becomes minus 1 over 5, 1 over 5, minus 1 over 10, and 0. And then finally I subtract them. So my matrix Z that I was looking for is minus a half plus 1 over 5. So let me write it here. Minus a half plus 1 over 5. The other one is minus a half minus 1 over 5. 1 over 4 plus 1 over 10. And then minus 1 minus 0. So if I want to simplify this, this becomes 3 over 10. The next one is minus 7 over 10. So the next one is 14 over 40, which becomes 7 over 20. And the other one is also minus 1. Yes? So 14 over 40 is, yes, that's correct. So this is the other matrix that I was looking for. Okay? So now we have all of our matrices and then we are done. Okay? Oh wait, I made a small mistake here. minus a half plus 1 over 5 is not positive 3 over 10. It's negative 3 over 10. Sorry. Okay, finally the last problem, problem F. Let m and n be positive integers, and let e sub ij, where I and j are positive integers, such that I lies in this interval from 1 to m, and j lies in this interval from 1 to n, be an m by n matrix whose entries are all 0 except for one entry, and that entry is the ijth entry, which is equal to 1. First, show that any m by n matrix A can be written as this double sum. Inside this double sum, you see that these are the entries of my matrix A, and Eij's are the matrices defined here for me. And then write this matrix in terms of Eij matrices defined above. Of course, this last part is easy because if you already have proved this formula, you can use this to write this in terms of the E matrices. Actually, it tells you that any matrix A can be written in terms of these matrices. One thing that I want to mention is that I hope that you are not confused with this notation, and you are not confusing this notation with this one. Here, my matrix, the name of my matrix is E, and I am interested in the ijth entry of that matrix. But here E sub ij refers to one single matrix. These are not the entries, this is the name of a matrix. Okay? This problem is much simpler than it sounds. Okay? Of course, this is the nature of mathematics. If you want to write something rigorously, sometimes it sounds difficult, but the idea behind that is very simple. And then you need to improve this skill in yourself to be able to decipher actually what is behind these sentences. And if you're going to have a career in the future which is somehow related to mathematics. Okay, one possibility for better understanding the problem is to consider a particular case. Here we have different parameters, m, n, and I and j. Okay, so to be specific, let me start writing something with the blue color. I don't want to solve this problem in its full generality in the beginning. I want to consider a particular case to see that this problem is actually very, very simple. So instead of proving this for the general case, let me consider a particular case. Say, let me choose 2 for m, and let me choose 3 for n for the time being. Okay? And then what are these indices I and j? According to the problem, I is an integer in this interval. So here, I is an integer which goes from 1 to m. M in this case is 2, so it goes from 1 to 2. It's an integer. J goes from 1 to n. N I have chosen to be 3, so j goes from 1 to 3. So it means that the choices for I that I have are actually... The choices for I that I have are 1 and 2, and the choices for j that I have are 1, 2, and 3. So if I want to concentrate on this combination ij, I will have 6 combinations, yes? I can choose 1 for I, 1 for j. I can choose 1 for I, 2 for j. I can choose 1 for I, 3 for j, and the same thing for 2. So 3 cases for 2. Okay. So it means that if I want to talk about these matrices, Eij, for this particular case, I have 6 of them. Okay? So all of them are, according to this, all of them are m by n matrices. So in this case, all of them are 2 by 3 matrices. Okay? So let me try to write them down here for you. Okay. So I will have E11, which is a 2 by 3 matrix. Then I will have A12, which is also a 2 by 3 matrix, and I will write them all for all of them. And finally, E23 is this 2 by 3 matrix. But how should I define my matrices? I know that all these entries are 0 except one entry which lies on the ith row in jth column. So here I is 1, j is 1 as well. So the entries lying on the first row and first column is my exception, which is defined to be 1. Any other entries is defined to be 0. So this E11 is a 2 by 3 matrix in which this entry is 1, other entries are 0. Okay, how this is defined? Again, this is an E matrix defined to be a 2 by 3 matrix. All entries are 0 except one entry. That entry lies on the first row and second column. So first row and second column, yes. So this one is not 0. That's the exception, which is 1. Other entries are 0 here. Okay, so then this becomes 0, 1, 0, 0, 0, 0. And then you can immediately write the other ones similarly. Okay. So these are my E matrices that are available for me for the particular case in which M is 2, N is 3. Now, I want to show that any M by N matrix, any 2 by 3 matrix, can be written as this double sum. Okay, so let me start from the right hand side. So what I am writing is actually I am proving this equality for a particular case. Then I will talk how we can prove it. When we realize what is going on, we can prove it for the general case easily. So the right hand side is equal to a double sum. I starts from 1, j starts from 1, but you see I goes from 1 to m is 2 in this case, so I goes from 1 to 2, and j goes from 1 to n is 2, n is 3 in this case, so j goes from 1 to 3, and then I will have aij times eij. What are these entries? These are entries of an m by n matrix, 2 by 3 matrix. Okay, so let me take this matrix A to be A11, A12, A13, A21, A22, A23. Okay, so that is a generic 2 by 3 matrix. I want to show that if I calculate this, where these are coming from this matrix, it becomes the matrix A itself. Okay, so let us calculate this. The first thing that I can do is to expand these two sigmas. I goes from 1 to 2, j goes from 1 to 3, so if I write everything down in detail, so it becomes a11, e11, plus a12, e12, plus a13, e13, and then I will have a21, e21, a22, e22, plus a23, e23. Okay? So that is the expansion of the right hand side. But now you know these matrices, so instead of these E matrices, you put these matrices instead. So it becomes A11 multiplied by 1, 0, 0, 0, 0, 0. And then the next one is A12 multiplied by E12, but it is 0, 1, 0, 0, 0, 0. And then you can continue, okay? So let me just do it quickly here. Okay. But now these are numbers and these are matrices, yeah? So I multiply this by multiplying it to every entry in the matrix. But the entries of the matrix are all 0 except 1, so only one of them will survive in each case. So the first matrix becomes A11, others are 0. The next one, the same story. Okay, now I am supposed to add all these 6 matrices, so you know that you need to act component-wise. So I will take the first entry and add all these first entries together. But all these entries are 0 except the very first one. So if I add them, it becomes just a 1, 1. Okay, let us concentrate on the second entry. This one and this one, this one, this one, this one, and that one. So you see again, only one of them is non-zero in particular, so it becomes a 1, 2, and then you can convince yourself that the other entries are exactly these entries of the matrix. And then what is this? This is exactly the matrix itself. So it becomes matrix A, and this is equal to the left-hand side. Yes? So that is the proof for this in one particular case where I have chosen m equal to 2 and n equal to 3. But of course, I hope that you realize nothing is so particular about these choices. If I choose different numbers for m and n, the idea remains exactly the same, but the dimensions of the matrices actually changes. But nothing will change in principle. The reason that this is important in the future when I am talking about vector spaces, you will see that. So here we showed that any matrix can be written in terms of these E matrices. Later we say that these E matrices form a basis for the vector space of 2 by 3 matrices. Okay, so in the future that would be important for us, but I don't want to distract you for the time being with these concepts. Okay, so now let me go and prove the general case. Okay, now let us consider the general case. Again, for the general case, I have an m and n, and I know that I is an integer between 1 and m, and I know that j is an integer between 1 and n, and I want to prove this equality. Okay, so this equality is between two matrices. On the one hand, A is an m by n matrix on the left hand side, and on the other hand here, these A's are coming from this matrix, so they are just numbers, but these EIJ's, based on definition, they are m by n matrices. So if I multiply an m by n matrix by a number, it remains an m by n matrix. So this is an m by n matrix for all possible choices of I and j. And if we add them, it becomes again an m by n matrix. So the matrix on the left hand side is m by n. The matrix on the right hand side is also m by n. So from the order point of view, they are equal. So now I want to show that any entry of this matrix sitting on the right hand side is equal to the corresponding entry of this matrix. If I can do that, then I am done. Okay, so I need to concentrate on one entry here at a time and compare it with the corresponding entry here. Okay, I would say that let K and L be positive integers such that K is somewhere between 1 and m, and L is somewhere between 1 and n. Okay, now if I ask you what is the entry of this matrix EIJ sitting on the kth row and 11th column. So I want to understand this. So remember, this is the matrix. All its entries are equal to 0 except one of them, which lies on the ith row and jth column, and that is equal to 1. So you would answer to this in this way. You would say that the entries are definitely either 1 or 0 based on the definition. But when it becomes 1 if you are interested in the entry k equal to I and L equal to j. So this happens if k is equal to I and L is equal to j. And it becomes 0 otherwise. Yes. So 0 otherwise. Instead of otherwise, I would write k is not equal to I, or L is not equal to J. Yes? So this is the definition of the matrix. So this is clear from the definition of these E matrices. Okay, but I can write this in a very compact form using the Kronecker delta. Yes, I would say that this can be written in this form, that I can write it as delta Ki multiplied by delta Lj. Yes. Why is that the case? If k is equal to I and L is equal to J, this is supposed to be 1. But if k and I are equal, this first Kronecker delta becomes 1. And if L and J are also equal, this second Kronecker delta becomes 1. And if I multiply 1 by 1, it becomes 1 again. So this means that what I have written here is equal to 1 under these circumstances. But now assume that I is not equal to k. Then this delta, Kronecker delta, is 0, and 0 multiplied by anything, it becomes 0. And if L is not equal to J, then the second delta becomes 0, and again the product is equal to 0. So hopefully you are convinced that what we have written here is exactly this product. This will help us a lot not to write so much. Okay, so how? I will start concentrating on the entries of the matrix on the right hand side. I would say I want to consider the entry of the right hand side matrix which lies on the kth row and 11th column. Okay, so let us see what is this one. Okay, so if now here you see that I have a bunch of matrices added together, and I am interested in this entry of the sum. According to the definition, I can write it as I can concentrate on the entries of these matrices, of the corresponding entries of these matrices, and add them. Yes, I goes from 1 to m, j goes from 1 to n. But then we know that if I have a matrix multiplied by if I have the matrix multiplied by a scalar, a number, and I'm interested in the kth entry of that, I can simply write it in this form. I can write aij multiplied by the corresponding entry of this matrix, and I also have these double sums, so I will write them down. So it's sigma I goes from 1 to m, sigma j goes from 1 to n. Okay, but now I use this equality. So instead of this one, I can replace delta ki, delta lj. Yes, so I will continue, and it becomes sigma I goes from 1 to m, sigma j goes from 1 to n, aij, and then I will have delta ki, delta lj. Now hopefully this is very simple for you at this stage, because we have practiced these kinds of sums in the previous tutorial. Yes, so here we have a sum with counters I and j, and then we have two deltas. Okay, so for example, I can concentrate on this delta. There are two indices for this delta. One of them is L, one of them is J. And this counter of this sigma depend exactly on one of these indices, say J. So in principle, I can eliminate these two. Before that, by the way, I need to consider the second index to see if that is in the correct range. The second index is L, and L is a number between 1 and n, and what is J? J also is between 1 and n, so it means that yes, the second index is exactly in the range of the counter of this sigma. So everything is in order, so it means that I can eliminate this delta, I can eliminate this summation notation, but the price that I need to pay is to change J to L everywhere left. There is only one place that j is left, so this j should be replaced by L after these eliminations. Yes, so this becomes equal to the sigma I goes from 1 to m AIL and delta KI. And again the same story. I have a delta. One of the indices of this delta is the counter of the sigma. The second index is actually in the range of the counter. Why? Because k is between 1 and m, and the counter runs from 1 and m, so that's everything is okay. So I can eliminate this delta, I can eliminate this sum, but the price that I need to pay is to replace I with k everywhere left. But there is only one place that I is left, and this is here. So the answer becomes A KL. But another way of writing A sub KL is to say that this is the Kth entry of matrix A. So now look here. The Kth entry of this matrix, which is the right-hand side matrix, is equal to the corresponding Kth entry of this matrix sitting on the left. And this is a generic argument for all possible values of k and all possible values of n. So it means that I was able to show that each entry here equals to the corresponding entry here. So it means that this identity has been proven. So this is a very better and nicer way of proving this using the Kronecker symbol. Of course, the idea behind this is exactly as before. So if you want, you can write them as blocks of matrices and then convince yourself that it's this case. But of course, I told you this is very, very simple. But I prefer to use this Kronecker delta that we actually developed before. Okay, now the last part of the problem. The problem is that we want to write this matrix in terms of these E matrices. But of course, here I have a 3 by 4 matrix. Okay? So what should I do? I can use this formula. So what I need to do is just to write a sum of each entry multiplied by the corresponding E matrix. But of course, if I have the 0 entry, when I multiply 0 by that matrix, it becomes 0. So the only things that contribute to this sum, the only entries that contribute to this sum are the ones which are not 0. Okay, so I will pick up these numbers. Okay, so if I want to write that, then I would say that A is equal to the entry is 1. I multiply it by E. Which E? This entry is entry 1, 1. So this is E 1, 1. The next one which contributes is this one, but this is 1 multiplied by E 1, 2, because this is the entry on the first row and the second column. Then if I want to write, I need to write 0 multiplied by E1, 3. But of course, we know that this is the 0 matrix, and the 0 matrix is the additive identity, so it doesn't play any role. Okay, the next one is this one. So it becomes plus, again 1 multiplied by E. This is the second row, second column, so it becomes E2, 2. And then finally, I have E times E2, 3. Because the next one lies on the second row and the third column. And then these two don't have any contributions, and then, well, we have only these two. So it becomes 2 times E sub 3, and plus 2 E sub 3 in 4. Because this is the third row, third column. This is the third row, fourth column. Yes, so finally, if I want to write it compactly, so A becomes equal to E11 plus E12 plus E22 plus E23 plus 2 times E33 plus 2 times E34. Okay, so that is writing A in terms of E. Okay.
I hope that this video is helpful. If you think that it was really helpful for you, I would appreciate if you can give me a thumb up. And I will also appreciate if you can subscribe to my channel to support me. Okay, until the next video, be safe and goodbye.